My name is Ajay Singh. I'm responsible for product management for Nimble storage. So over the next 40 minutes or so, what I'm going to talk to you about is a breakthrough new approach to storage that Nimble's developed. What it leads to is a convergence of ice-fuzzy primary storage, backup, and disaster recovery in one elegant solution. Now, we did it by taking a fresh approach to storage and designing an architecture from the ground up that was optimized for flash-based SSDs and low-cost, dense, low-RPM SATA drives. Flash is obviously available from a number of storage vendors, but if you looked at any, you might notice that it's hard to justify the cost for most mainstream applications and for the typical mid-size enterprise. By taking this fresh approach to storage architecture, what we've been able to do is bring the affordability of flash down to the point a mid-size enterprise can consider it for mainstream application. The result is something that dramatically simplifies storage, improves the data protection, and at the same time leads to a significant savings in upfront cost. We've been around as a company for 3.5 years, and Nimble has been very fortunate to garner a growing list of customers. We're growing very quickly, as well as a long list of industry recognitions and accolades. So a couple of recent ones I'll mention. Gartner, who many of you probably recognize as an analyst firm, picked us as one of their cool vendors for 2011 in the storage area. The Wall Street Journal, which doesn't typically focus on early-stage technology companies, did a study of about 5,000 venture-backed private companies, and they picked a list of 50 they said were really compelling. And we were fortunate to be picked as number 17 on that list. Now, some of the reasons we're getting a lot of this recognition is people see what we've developed, the interesting technology, but it's also factors such as actual proof in terms of revenue growth, bookings growth. As a private company, we don't necessarily announce our results, but we do announce our milestones. And in January, we announced that at this stage of our growth, we were the fastest growing storage company in the last 2 decades. And that list includes a lot of very well-known and well-respected names. So it's factors like that that are generating a lot of interest in Nimble. So what I'm going to tell you over the next few minutes is a little bit about the people behind Nimble, who created it, why we created it, what problems we set out to solve. But since this is a technical audience, I'm going to respect that, and I'm going to spend the bulk of the time describing what is this new fresh approach, what is the new architecture. And I'm actually going to drill down deeper into 3 specific aspects of our technology that combined make us very different than any other storage solution out there. And I'll wrap up by describing, obviously, what that fits in virtualized server or virtual desktop environment. So our founders and our executives have a lot of storage DNA, a long history of working in early-stage storage companies that went out to be very successful and driving very successful architectures, file systems. Our VP of Engineering was employee number 11 at NetApp and saw it grow and helped its growth from nothing to a very successful enterprise storage company. Then he went on to become employee number 12 and the first VP of Engineering in data domain, which, as you probably know, revolutionized disk-based backup, a well-known name there. Similarly, our CTO has developed multiple file systems in his career, some very successful ones. Most recently, he was a technical director and architect at data domain. Our CEO led all of engineering and product management at NetApp for several years. I myself worked at NetApp for many years before I came over to Nimble. And we're backed by some really well-recognized investors. These are the people who backed a history of picking winners and backing companies like Apple and Google and Cisco and Oracle and Facebook and Riverbed. And these people pick good teams, they look for good ideas, and then they back them. We're based in San Jose, California. That's where all of our engineering and support staff is. So let me talk a little bit about what are those problems that led us to found Nimble Storage. But before I do that, since we're at a VMware event, I wanted to throw out a bit of trivia. I wonder if many of you recognize the people in this picture. It's two of the founders of VMware. So there's Diane Green and Mendel Rosenblum. They founded VMware in 1998. But Mendel actually did something in 1992 that has a very direct link with Nimble Storage. This was way before they were thinking about VMware. And it's just a happy coincidence. If any of you know what that is, hold that thought. If you don't, I'll tell you about it in a few minutes. So, when our founders left their prior jobs, they had this idea. They had seen the emergence of storage architectures like NetApp's Waffle. They had helped drive disk-based backup architectures like Data Domain. They saw each one was solving a set of problems pretty well. But they saw that nothing was solving both sets of problems in a very elegant manner. It's primary storage and backup. At the same time, they saw three technology trends that would allow them to do something that was different and fresh and solve the problems in a better way. And those three trends were the growing adoption of low-cost SATA drives in the enterprise. That's been happening for a few years. The rapid emergence of multi-core CPUs, as opposed to just CPUs getting faster. They're not getting faster so much now as that adding a lot of cores. But the biggest disruption they saw was the emergence of flash-based SSDs, and they saw a way to develop a storage architecture that can do things better if you took advantage of all of those three. So to back up and describe those industry problems, here's a view of the typical storage backup and DR environment about 10 years ago. So in about the 2000 timeframe, if you were a mid-sized enterprise, you probably had something resembling this. You would buy a modular storage architecture, typically from a market leader like UC or IBM or Hitachi. Now modular meant you chose your controllers, and then you stacked shelves of drives underneath those controllers. So what was wrong with that picture? You had to think ahead about what your performance and bandwidth and CPU needs might be, not just today, but for a couple of years or 3 years down the line. Because once you bought those controllers, you were pretty much locked in. Moving away from those was an expensive and painful proposition. So you did a sizing exercise, you bought a high-end or a mid-level or entry-level controller or pair, and then you started just stacking shelves of drives. Drives typically meant, for your primary applications, 15K or 10K RPM fiber channel drives. It was the only way you could get IOPS, or sufficient IOPS. Now that was unfortunate because on a dollar per gigabyte basis, these higher RPM drives cost about 5 times as much as low-cost, low-density SATA drives. But you didn't have any other choice. Backup typically meant going to a tape library. It was a process that was driven by backup software. The backup software would look at the application servers, identify what's changed in the last day, start copying the data off during the night, and on a weekend you did a massive bulk copy of everything, just so you didn't have too many incrementals building up. So the problem with that was obviously bulk copying data means you're swamping your application server and your network and your backup device. So you don't want to do it during the course of daily operations. You have to find a backup window and do this at night. And then if you do need to restore something, you were looking at identifying the right media, plugging them in one by one, rebuilding your primary data set, probably looking at several hours. So it was painful. Disaster recovery, primary application did exist at this time. It was expensive. So most people, for most of their data sets, were relying on a mountain truck to take away their weekly backup tapes once a week and store them in an archive somewhere. So the problem with this picture is not that it was super expensive necessarily. The primary storage was. The backup and the DR wasn't so much the cost, it was the pain of managing this backup process. And the fact that it was all driven by this heavy-duty copy process up front, which meant you couldn't do it many times a day, which meant your recovery points were typically no better than 24 hours. Recovery times were also really poor because you had to coalesce a lot of incremental backups to get data back. Now, the good news is a lot changed in the last 10 years. In the primary storage area, a number of storage companies have entered the market, become remarkably successful, and most of them have been acquired using a concept called scale-out. The idea is don't make the user choose up front whether you're going to need a high-end controller or mid-range or low-end, and if you guess wrong, then you're stuck with something you can't easily migrate from. Instead, the picture is you buy a node which contains CPU, networking, some memory, and some storage. And then if your needs grow, you cluster another node. So not only does your capacity grow, your performance grows at the same time. Challenge was that engine of your performance was still pretty much that hierarchy and fiber channel drive, so the 10K, 15K drive. And the cost delta between that and a SATA drive was still about 500 or 600%. Still an expensive way to get performance. Backup did change a lot in this time frame. I told you where our founders came from. They had a lot to do with this. Disk-based backup became very cost-effective. VTLs had started to do that, but once you could deduplicate your backup images on disk, it really became cost-effective to keep 30, 60, 90 days of retention on disk. So you wouldn't have to go to tape very much. If you did, it was more for archive purposes. What didn't change was your copy process. Everything was still driven by a backup application, looking for what's changed, doing this massive bulk copy, which typically takes several hours or all night every weekday, and then anywhere from Friday afternoon to Monday afternoon on the weekend. So recovery points didn't get better. Recovery times got a little better. You're no longer plugging in tape media into the library. It's all on disk, but it still takes a few hours. Disaster recovery, you've got another option here in the mix. So primary replication was expensive because it took a lot of bandwidth, but backup dedupe-based replication was cheaper because it had already done the hard work of collapsing a lot of your backups down, finding only changed data and keeping them on disk. It was only a small step from there to replicate it to another device. Very RAM efficient. Good news for WAN. Bad news, recovery points and recovery times. So bad. So when you needed your data back, you're at least looking at losing 24 hours of data because you haven't been doing backups every hour. And you're looking at restoring from this tower-based backup software format to something your applications can actually run. So this was the picture when our founders conceived of the Nimble architecture. And what we've done is basically take the equivalent of about 3 shelves of high RPM drives. So imagine 3 shelves of 15K RPM drives. And the IOPS you would get from that and the capacity you would get from that. Plus another disk-based backup device with sufficient capacity to back up about 60 or 90 days for that primary data. Imagine a device that collapses that all down into a pretty dense package, about 3U high. That was our first product. Now, how we did it, at a high level, I described it on this slide, and I'll dive right into it. We did it by combining, as I said, commodity flash-based SSDs and commodity low-cost SATA drives, but with an architecture that really meshes them together very elegantly. So you get performance mostly out of flash, and your capacity mostly out of SATA. Plus, on top of that, we threw in some things like inline compression, and very, very efficient backups using Delta snapshots. So now, these snapshots have very little capacity impact. It turns out they also have almost no performance impact. So you can afford to do that every few minutes. So instead of that backup process running nightly, you can be doing snapshots every 15 minutes, replicating them every hour, and keeping hundreds of thousands of them. So keeping 60 or 90 days of snapshots cost effectively. And you could always keep a lot of snapshots if you have the money. Most people never did. But you can do it with this. As I mentioned, those snapshots, now that they're block level deltas and contrast, you can afford to replicate them pretty efficiently, not hog a lot of RAM bandwidth. So the picture is you collapse a lot of boxes down into something smaller, more cost effective. The really exciting thing is you've eliminated one of your most painful daily headaches, which is your backup window. And at the same time, you improve your recovery time and recovery points. So now, how do we do this? The architecture looks like this. This is a high-level block diagram, and I'll dive into some of the components in a minute. So the three layers are a thin-line compression layer, a large flash cache layer, and a big disk layer. So if you imagine those red blocks on top are blocks of data coming in from your applications. You know they tend to come in random order, so this is random write. First thing we are able to do is compress those blocks of data inline without adding latency or without impacting IOPS. So that's a big difference compared to anything else out there. Compression as a feature, sure, it's available. It's been available on backup devices forever. It's even now available on primary storage, but it comes with a lot of caveats. Don't use this on performance-sensitive applications. One of the big things that lets us do this, the obvious thing that people think about, well, yeah, you have multi-core CPUs, so that's why you can do compression, right? It helps, but that's not the big reason. If that was the reason, everyone would be trying multi-core CPUs at their storage and trying to do faster compression. The big reason we're able to do this for random data is we can natively support variable block sizes on disk. And the reason that's important is compression is an inherently variable process. If you have a ESX data store writing 4 kilobyte blocks to disk, you might compress some of them down to 2.1 kilobytes, some to 1.8, and some not at all. If you're trying to put them on fixed slice slots on disks, you're either going to waste a lot of that slot, or what really happens in the real world, people try and group these 4K blocks together, try to compress them down into an integer number of fixed slots on disk, so they can squeeze them into this fixed slot. Either way, you're either wasting space, or in reality, you're really impacting performance. If you think about this picture, if you take 8 blocks, compress them down to 6, put them on your 6 fixed-size blocks, and now your ESX or your SQL database needs to modify any of those 8. You've got to read all of those back, decompress them, modify it, recompress all 8, and write them again. It's a huge IOPS impact, which is why they don't recommend doing this. So that's the first thing we do that's different. The second thing we do is we collect a lot of these variable blocks in non-volatile memory until we've collected a big stripe. So rather than push individual blocks as writes to disk or flash, we collect them in big stripes. There's an important reason for doing that. The physics of SATA drives and the physics of flash have one big similarity. If you start writing to them in random sequence, their performance really degrades. And in the case of flash, even the lifespan degrades. For SATA drives, here's a very simple way to think about it. If you're writing 4 kilobyte random blocks, you can get about 50 IOPS. Multiply 50 by 4K, or you've got 200 kilobytes of throughput. If you can expand that stripe size to a megabyte, a SATA drive can handle 100 megabytes of throughput. Think about that ratio, 200 kilobytes to 100 megabytes. It's a factor of 500. So depending on how you use SATA drives, you can get tremendous performance out of them. The way to do that is to sequence a lot of these random blocks together and write in messaging stripes. I'll describe in a slide or two why others haven't done this. There's a reason for that, and why we are able to do this. Same thing happens with Flash. Flash has this physical concept called a raised block. You can write a 4K block, but what it's going to do under the covers is erase a much bigger chunk, say a megabyte, and then replace that 4K and then write everything back. So it's doing a lot of extra cycles just to write a random block of data. If you do that too many times, performance degrades, and it's going to die in a year as opposed to 5 years. So by doing this, we get the best out of both kinds of media. Flash is typically used just for random data. We have a lot of intelligence built in by knowing the application, knowing the I/O pattern, whether the data is worthy of belonging in a flash cache or not. And we have an index that monitors each 4 kilobyte block of data to see, has this been read, is it likely to be read, if not, flush it out of cache. And we can do that within milliseconds. So Flash is just a cache. And I'll come back to why that is an important benefit later. So data is always written to disk, may or may not be written to Flash at the same time. Now once you've got compressed stripes of data on disk, it's an easy step to then add delta block incremental snapshots, which also has the benefit of compression. So you've got very cost-effective local backups on disk. So, combination of those two things has given you very good random write performance, very good random read performance, because Flash is the main mechanism which is serving your random reads, and very good use of capacity. The last step is you just replicate those delta and compress snapshots to the second device, and you've got a complete data protection solution, because you probably do want a copy of the data on another device, ideally in a different data center or a different city altogether. So now you've got your performance needs, you've got your capacity needs, you've got your local backup needs solved, because most of your backups are going to come from the same box. But if the entire rack fails or your sprinklers go off and the box fails, you've got another copy of your data somewhere else. Now, imagine if you had a Flash architecture you've been shipping as a product for 10 or 15 years. You've done a pretty good job optimizing it for high RPM drives, and maybe even optimize it somewhat for low RPM drives. And suddenly in 2007 and 2008, Flash-based SSDs start coming around to the market. What do? You can still take advantage of that. You do that in one of two ways. What's more common is you add Flash as a tier, meaning some data sets go to Flash first. You serve your writes fast there. You watch if that data is going to be read. If not, a few hours, a few days later, you move it slowly using some tiering engine to lower cost disk medium. It works. It's an easy way to add Flash to your architecture, and you still get some benefits, because on a dollar per IOP basis, these Flash drives are better than 15 KRPM drives. But there are some downsides. One, because your random writes are going to Flash, you have to use the best kind of Flash there is. It's called enterprise Flash or single layer cell Flash. On a dollar per gigabyte basis, that's 3 to 4 times more expensive than the kind of Flash you might have in your laptop, which is multi-layer cell. Second, because it's a tier, which means there's some data that's only in Flash, so you've got to RAID protect it, otherwise you risk losing it. So you're going to do RAID 1 or RAID 1.0, because you bought this very expensive thing for performance. You're not going to kill its performance by doing RAID 6, so you're going to do RAID 1.0. Sure enough, that's what all vendors recommend. So suddenly you've lost another 2x capacity. Plus, as I mentioned, none of them can do compression in line on this tier. So you lost another 2x compared to what we can do. So you add all those up, or rather multiply all those out, and you can see how using Flash as a tier works. It actually gives you pretty good performance, but it's expensive. The second downside is this tiering engine. You don't want to do this tiering at 4K granularity. It's very expensive to keep the metadata at 4K granularity. So typically they do it at a much bigger granularity. Hundreds of kilobytes or megabytes is very typical. And the cost of moving is it's a big cost, because you've got to recompute rate on both sides. So you don't want to do this just because the data hasn't been read for a few seconds or a few minutes. You want to watch that data for a few hours and then do it. So you're going to have to over-provision your Flash, because the data is going to be there for a day or two. The other approach, which some other vendors have taken, is to use Flash as a cache. Also works. The advantage there is you can use it to handle disk metadata and to read data. It's a read cache. It's just like extending very large DRAM. Instead of a few megabytes or gigabytes, you got tens of gigabytes. Problem is, because you've added it after your data architecture existed, you haven't done anything to change the layout on disk, which means you haven't done anything to change the way writes are happening. So your write performance is still dependent on what kind of disk you're using. So if you have a workload that has 30–50% writes, or like VDIs and even more, you're going to need higher RPM drives still. So Flash can accelerate your reads, but it doesn't do much to accelerate your writes. Now, what if you were someone like us that was designing our architecture knowing Flash SSDs were available? What would you do different? What we've done is we still use it as a cache. But knowing that Flash is going to be there to take care of random reads, we can optimize the heck out of the way we write data on disk, and optimize the layout on disk purely for writes. And it turns out you can do a lot better if you do that. So We call it a sequential layout on disk. And then we have a lot of intelligence built around how to manage that sequential layout. So now, let me back up. I asked that trivia question earlier. Did anyone here know what that connection between us and Mendel is, the VMware founder? You have any idea what he did in 1992, which might have a link to this sequential layout on disk? Okay. Well, he wrote a paper as a PhD student and then actually implemented a prototype of a log structured file system. They did this as a research experiment. The thought process was, what if disks only handled writes? It was a thought exercise. Could you get better performance out of disks? And you can. If you log structured write, which is basically what I described, you collect a lot of random writes together, stream them out in nice big sequential chunks. Turns out you could get very good write performance. But of course, that experiment shut down a couple of years later. There were two reasons for it. One, you still wanted to read. And at the time, read caches were insanely expensive. When you think back to a PC or a server you owned in 92 or 94, you were lucky if you could get a few megabytes of cache. And the other reason was designing such a file system turns out to be pretty complicated. And this was a research group that were trying to build a product. So the connection with us is, in 2010, we started shipping the first primary storage product that's based on the log structured file system. It uses disks primarily to optimize the heck out of write performance, knowing that we've got this very large, today, pretty cost-effective flash cache to optimize random reads. That's the, I'm not sure if Mendel knows about us. I'd be pretty happy to hear what he thought of as a PhD student has finally become a successful shipping product. So let's talk a little bit about that sequential layout. There's three kinds of data layouts today. If you buy a primary storage device, you're likely going to see one of these three. The most common one is called write in place. It's used by the traditional SAM vendors. What this says is you have LUNs, you have block offsets or block numbers on disk. When the application writes block 3 on LUN X, it goes to the same location, it goes to block location 3 on the LUN. That actually means it goes to the same physical location on disk. Struct, of course, but it's the same physical location. So why do people do this? Because it actually is the simplest architecture to design. What's the downside of doing this? Well, imagine random writes coming in all kinds of sequences. Because they're going to random order locations on disk, your physical disk heads are going to seek around like crazy, trying to do all these random writes. You can try and mitigate some of this using a big write cache, but you're still going to have to write in random sequence. So random write performance suffers. You compensate by buying stacks of hierarchy drives and getting a lot of spindles behind the problem. The other approach, first popularized by NetApp and more recently by ZFS and Sun, is called a write anywhere layout. This breaks the link between the logical block location and the physical location on disk. What this says is, just tell me what random blocks you're writing. I'm going to try and collect them into stripes and write them out where I think is easier to write out. So if the head was going to be seeking somewhere, I'm going to write that there. Make sense? The advantage is you do get some good write performance benefits, at least early on. The problem is, over time, your volume fills up. You may be deleting data somewhere else in random holes, but you get the Swiss cheese pattern now. So now you can't afford to just go write big stripes. You've got to go back and fill holes where you can. So write performance has started off pretty good, degrades as your file system fills up. This is generally a knock against write anywhere file systems. They try to compensate, they do cleanup processes at night, but those are pretty heavy duty. They're like deep fat processes. We take it one step further. Oh, I should back up. The advantage I mentioned about our variable block size, the flip disadvantage for either of these approaches is because they have fixed block sizes. I mentioned earlier, you can't do compression in line and still expect good random performance. Our approach is to always write with stripes. So imagine the file system looks like this. It's partially empty, and in between there are some holes. You'll notice that the block sizes are variable and they're collected in stripes. So as data comes in, you keep writing big stripes. But notice something that happened there. In the background, we know where those dead spots on disk are, and we have a very optimized lightweight process that's running in the background that collapses the dead spots down and forces the creation of clean stripes all the time in the background. So where you had the Swiss cheese pattern, while you were doing your normal I/O, we cleaned up the Swiss cheese pattern in the background. This is something we designed from on day one. Now, if you look into the details of this, it turns out having a large flash cache also really helps with this process, this lightweight background cleaning process. So not only do we have very good random write performance, that performance doesn't degrade as the file system fills up. It's consistent random write performance. This is an important factor. Plus, I mentioned you can get very good compression. So that's the sequential layout story. So I've talked about two aspects of our architecture: how we use flash, that's different than others, and how we lay out data on disk, that's different than others. The third aspect is how we do snapshots. Normally, when you hear snapshots, a lot of people say, yeah, I use snapshots. How long do you keep them? A day, 2, maybe a week. Why don't you keep snapshots longer? It's typically one of two reasons. One, they start to impact performance. This is more true of copy and write snapshots. Every time you take a snapshot, the more often you keep, your performance degrades. You can't handle as much I/O. For us, performance doesn't degrade at the time of taking a snapshot, and whether you keep 1 or 100 or 10,000 snapshots, you can still keep serving the same I/O. What that means is we can do a lot of frequent snapshots and keep a lot of them. So recovery points, this is the reason we can do this. Honestly, the other reason people haven't traditionally relied on snapshots more is the cost. They're on expensive disk, plus they chew up a lot of space. This is the other reason we're better. If you imagine your database writing of just one 4 kilobyte block of data, on the left you have a traditional architecture, on the right you have Nimble. A lot of traditional architectures, instead of just capturing that 4K, actually capture a page of changes around that 4K. So even if only 4 kilobytes has changed, in some architectures you lock as much as 50 megabytes in a snapshot. That's a huge overhead of data that really shouldn't be in a snapshot that's being captured. Not only do we only capture chain data, as I mentioned, it's also compressed. So it's a big difference. So the snapshot space consumption is dramatically different. Plus, it's on a low-cost SATA drive. In fact, here's a real-world example. We set up an Exchange 2010 production database with 2 DAGs, one on us, one on another iSCSI system. In fact, it's a market-leading iSCSI system. And then just took snapshots, daily snapshots for 10 days. Now, we've done this experiment many times over, and the answer is always the same. After 10 days, our system was using about 1/25th or 1/30th the capacity for snapshots of this other iSCSI system. That's not a few percent, it's not a factor of 2, it's a huge difference. That's the reason we really promote and recommend our customers rely on snapshots heavily in our system, because it doesn't cost too much. So let me net out the performance and efficiency gains from those 3 things I was talking about. Performance gains, obviously, you get much better latency because writes are being acknowledged in memory, reads are coming from flash. Either way, you're looking at latencies on the order of hundreds of microseconds, not on the order of milliseconds. Second, the random writes have been coalesced, so you get much better random write performance. Just as a data point, in that 3U form factor I had mentioned earlier, we can get anywhere between 11,000 and 15,000 random IOPS, depending on the read-write mix, at a 4 kilobyte granularity. So most people do IO with 4K and tell me what your IOPS are. We're going to be somewhere between those two. If it's write heavy, it's going to be closer to 11,000. If it's read heavy, it's going to be closer to 15,000. most applications will be probably somewhere between 12 and 13. That's 3 form factor. The other advantage, obviously, is you could get that kind of killer performance if you stack a 3 form factor with just flash drives, but you'd only get a terabyte or 2 of capacity. That'd be a very expensive way to get those IOPS. We're getting roughly 32 terabytes with compression capacity in that 3 form factor. How are we getting it? It's through compression, the fact that it's coming from low-cost, high-density SATA drives. And if you choose to take advantage of snapshots, then highly space-efficient snapshots. In fact, if you have a 2% change rate, which is very typical for many SAN applications, and you're getting about a 2x compression, that's 100x advantage versus doing full copy backups. Of course, most people don't do daily full copy backups, but that just gives you a comparison point. That's all about the efficiency story. Let me talk a little bit about how an administrator might actually deal with all this, and how easy this is to set up or not. So we spent a lot of time studying what the IT team in a typical mid-size environment looks like. Of course, if you're a Fortune 50 company and you've got thousands of people in IT, you have a luxury of super specialization. Most people we sell to don't. They have more generalist teams. So what we did, first thing, was spend a year understanding the IO patterns of a lot of applications. SQL, 2005, 2008, Exchange, 2003, 7, 10, ASX4, ASX4.1, and so forth. And instead of making you the SAN expert, and you buy a box, plug it in, cable it up, first thing you need to do is just, I want to put some data on it. It just asks you with a drop-down list, what kind of data. So you pick, I want to put ESX 4.0 data store on this. We take care of optimizing everything about the storage for that application. You don't have to know block sizes, caching policies, what kind of snapshot schedule. We recommend one of each for you. So with 3 clicks, you're done creating the volume, optimizing it, and having its snapshot and replication schedule set up in a way that we think is most common. Any of those policies can be edited, but the point is, you're probably not going to have more than a handful of templates. You may have hundreds of volumes and data sets. You're probably going to have only a few classes of data. So by allowing you to use templates instead of typing in one parameter after another each time, we really simplify the steps in provisioning storage. You get the best performance because we've done all the hard work understanding the I/O patterns and what caching policy and block size make the most sense. The other thing we've done is integrated our snapshot capability with applications and hypervisors. Snapshots are most useful if they're application consistent or hypervisor consistent, so you don't have to do a lot of consistency checks if you do need to restore. So we've done that with VSS, so your SQL database or your Exchange database could be captured in a fully consistent manner. Similarly, we've done the integration with vCenter APIs, so your VMs are captured in a consistent manner. So when you need to do a restore, the rollback can be near instantaneous. If you don't want to do the rollback, you can mount a snapshot and then selectively restore data. Again, it's a matter of seconds or minutes. And then we do one other cool thing. For provisioning, especially in the VMware world, whether it's a virtual server farm or virtual desktop deployment, often you have a gold image or template and you want to clone it many times. We have a zero-copy cloning capability that gives you fully functional rewritable copy or clone of your data set without copying the data. It does it using a set of pointers. Think of it as equivalent to a pointer-based snapshot. So if you have a Windows VM and you want to clone it 10 times, instead of 40 gigabytes times 10, you're probably going to have 40.1 gigabytes of space. And it's all going to happen almost instantly. But that's a real benefit in VMware environments because we typically do clone the same thing many times over. So these are some of the examples of how we also try to make it simple for the administrator. Now, the biggest simplification, honestly, was you don't have to manage backup agents the way you used to. You don't have to manage a backup window or a process, which used to cause a lot of headaches every night. Replication course, I mentioned that it's event efficient, and that's based on how we capture the delta changes. But it's also very useful. I mean, it gives you a lot of functionality you expect from primary replication. So, for example, you can have 2 devices on 2 sites. Each one could be serving their own applications and VMs while serving as disaster recovery protection for the other one. So the out box isn't the dumb box. It can serve primary data. If you have a few ESX hosts or database or 2 in your VR site, by all means use that functionality. We allow asymmetric retention. So if you want to keep a few weeks or a week of retention on one site and 3 months on the other site per volume, you can choose that policy. So it's not like all the data here is replicated to all the data there. It's selective replication. If your sprinkler goes off and the primary storage device gets shut down, but you had hosts or clients available and wanted to access that data, you can fail over within a few seconds or at most a few minutes to that DR site and start accessing that data, not just reading it. You can read, write, modify that data. And when that primary device comes back up, you can resynchronize all your changes back. And this is a one-click failover and failback process. Now, to be fair, this functionality, failover, failback functionality, does exist with most primary application products you would buy from an enterprise vendor. It's just that we've paired it with something that gives you a lot more cost benefit and it's a lot simpler to use. And we support topologies like end-to-one. So if you have a lot of remote sites, you want to replicate a lot of them back to one central data center, we support that topology. So you can get that benefit as well. So what does all this mean in a VMware environment? If you've been following along, a lot of the benefits should be pretty self-evident by this point. Number one, all those IOPS, that compact form factor, give you a pretty safe way to serve very performance-hungry applications. You can virtualize them. Furthermore, if you have the ability to consolidate them on pretty beefy servers, part of the reluctance in the past used to be, well, I don't know if that's going to do my storage. And we take that fear away. You can consolidate a lot of VMs, a lot of virtual servers into a pretty dense form factor. Similarly, if you're planning a virtual desktop rollout, we know by now those can be pretty IOPS hungry. They can have issues like 9 a.m. boot storm. A lot of times your project gets bogged down because when you price out the storage, there's a little bit of sticker shock of how much you're going to need. And this gives you a very cost-effective way to get all those IOPS. Second benefit, obviously, is big storage savings. The compression rates do vary by application. For databases, we get something that's typically 2 to 4x. For ESX VMs, it depends a little bit of what's in the VM, but we reliably see about 2x or 50% compression. So you get pretty good space saving. Plus, as I mentioned, if you have a gold image or a template, you get even bigger space savings by cloning it without taking any incremental disk capacity. And then snapshots give you a lot of capacity savings, certainly compared to any other backup scheme. If you're comparing to any other snapshot scheme on primary storage, this, I can tell you, there's nothing else that's more efficient than our snapshots. This is the part that's easy to claim. Everyone claims they're simpler. It's kind of hard to justify or prove. I described some of the ways we do this. It's all template driven. So you're not manually repeating a lot of processes that you do repeatedly. Instant clones, really simplified provisioning, rolling out the same image many times. And eliminating backup management is another big time savings. But I will confess that for a lot of people, this point is only proven when they see a demo. And, if that's something that you like to touch and feel something before you believe such claims, all power to you. It's a great demo to see. Finally, compared to any traditional backup scheme, your data protection actually got better because you can afford to take very, very frequent snapshots and very frequent replicas. So your recovery points got better and your recovery times got better because rolling back a snapshot or mounting a snapshot is a very, very quick process. There's no restore to application format required. The quick failover of an entire VM farm, we can do this at a collection level. We can define this as a policy. We can one-click failover a big farm of VMs to another site if you wanted to. And then fast failover, fail back again, that helps improve your recovery times. So I'm going to wrap up here. I mentioned we're the fastest growing storage company, at least at this stage of our growth, in at least the last 20 years. We have a very fast growing list of customers. And if you look at some of the logos on there, you'll see it's not that they're specific vertical, it's not that they're just very small or very large. We did target mid-sized enterprises, but we actually have customers that go much below and much above that. Verticals span anywhere from high-tech to financial services to manufacturing to retail, state and local government. But some of the threads that are common across all of them is they liked how they could get very good IOPS for their primary applications and VMs. Turns out somewhere between 85 and 90% of our customers are using us in some VMware context. We have a few more percent using us for Hyper-V or Zen, but VMware is by far the biggest application, so to speak. The other thing they liked about us was that capacity was very, very cost effective. So the compression and the cloning and the snapshots give you very cost effective network. And finally, it gave you a very elegant and simple way to improve your data protection. So those are the three reasons why we're doing really well. Now, the emergence and the rapid adoption of VMware has been a big benefit to us. We can ride that trend by having a very, very good solution for that trend.